Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss approximating derivatives using interpolating polynomials. So in this topic, we will find different formulas for approximating the derivative and the second derivative. We will use information first on both sides of the point, and then only use information to the left of the point. So we will find interpolating linear polynomials, interpolating quadratic polynomials, and interpolating cubic polynomials. We will then see that the formulas that we derived from these interpolating polynomials, which are then differentiated appropriately and evaluated at particular points, have formulas that depend on the step size between values. We will note that the order h squared formulas converge more quickly as h is made smaller, as having h will actually reduce the error by a factor of 4. And we will discuss the differences between the formulas and look at examples of each of them. Now, in the previous topic, we looked at taking discrete data points that come from, for example, sensors that are periodically read, and we tried to estimate the value of functions between those points by using interpolating polynomials. In this topic, we're now going to try to estimate the derivative or second derivative at the point x sub k or t sub k. Now, in the first case, we're going to have access to information or samples of the function both to the left and to the right of the value x sub k. However, in the second, we are going to assume that we are at the time t sub k now. We have the most recent data point, but we only have access to previous y values. Now, we're going to be comparing different estimators of the derivative, and so we're going to have a consistent step size h. Thus, while normally we would use t sub k is equal to t naught plus k times delta t, for this topic we're going to stick to t sub k is equal to t naught plus k times a step size of h. In your calculus course, you learned that the derivative of a function is the slope of that function at a given point. Now, suppose that we have these 2 points here. So we have the value of the function at these 2 points. The slope of the line that interpolates these two should be close to the slope of the function at the point x sub k. So there is our interpolating polynomial, and the slope of this line is given by this expression over here, rise over run. All right, so given this expression of the slope, we note that x sub k plus h is equal to x sub k plus 1, and therefore the difference between these two x values is h. Thus, the formula that we just deduced is equivalent to the formula you saw in first year, and the derivative is the limit as h approaches 0 in this context. However, unfortunately, we're periodically sampling data, so we cannot reduce h, at least not by too much. So instead, we only have a finite approximation of the derivative. So what is the error of this approximation? We have the slope of a function, or a slope of an interpolating polynomial. How closely does that approximate the slope of the function at x sub k? Now, the only formulas that we have right now that describe error are the Taylor series. So here's the Taylor series of f at x sub k plus h, and it is a first order Taylor series. What we can do, however, is let's move the derivative to the other side, bring f at x sub k plus h to the right-hand side, and let's negate both sides. If we do those steps, we now have this expression here. Now with this expression, we can divide both sides by h, thus isolating the derivative. And now we have that, the derivative at x sub k is equal to this approximation we just calculated with the given error term. Now here, psi is some value between x sub k and x sub k plus h. Therefore, we have the following approximation of the derivative, and we even know the error. Now, the error is a constant negative a half, times the second derivative evaluated at some point between x sub k and x sub k plus 1. Now, in all likelihood, the second derivative is not going to be too wild, and so we can probably assume that the second derivative of f is probably approximately constant on that interval, or at least not changing too rapidly. However, in any case, we still don't have any control over the second derivative, so the only way we can reduce the error is to reduce the size of h. All right, so since the error is multiplied by h, then if we want to reduce the error, we need to decrease the size of h. Well, the only way we can do that is by increasing our sampling rate. So, for example, if we double the sampling rate, then the value of h, the distance or time between samples, is reduced by a factor of 2. And therefore, the error of our approximation is also going to be approximately halved. At the same time, halving the sampling rate, which is therefore cheaper, is going to double the value of h and thus increase the error by a factor of 2. All right, let's say we want to approximate the value of the derivative of sine of x at x is equal to 1. So we're going to have different values of n. N will then define h. H will be 2 to the negative n. We will have our approximation using our formula of rise over run. We will then print out the error and see what the error is according to the definition. And again, that's based on negative 1/2 times the second derivative of the function evaluated somewhere close to the point x is equal to 1. We don't know where that point is, so we're just going to substitute the value of 1. But this will be multiplied by whatever value of h we are currently using. So when n is equal to 1 and h is equal to 0.5, our approximation of the derivative is 0.31, which is not that close to 0.540 and change seen below. The error is quite large, but you can see that a half sine of 1 times this value of h is actually not a bad approximation of that error. All right, let's have h. Okay, you can notice that the approximation seems to be getting closer. The error is going down, and yeah, the estimation of the error is also apparently correct. Next, let's take the ratio of the current error over the previous error. We said that the error should drop by a factor of 2 if we have h. And we notice that the ratio between the errors is approximately 1/2. Dividing h by 2 again we get a better approximation. The error goes down. Notice 0.1102 is the previous error. 0.05393 is the next error, which is indeed approximately half. And once again, our formula does correctly predict it. So now it's even closer to being half the error. With the next one, once again, better approximation, and again, the error has dropped by even closer to being a factor of 2. A better approximation, and the error is again dropped by half. We carry on and note that with each step, the error is dropped by a factor of 2. All right, so that's pretty good. And our estimation of the error has gotten pretty good because our estimation of the error is correct to almost 4 digits. Now, we still have a poor approximation of the derivative. It's not that great. The relative, well, yeah, it's not that great an approximation. Question, can we do better? Well, suppose we find an interpolating quadratic that passes through 3 points. Well, if we have a quadratic, we know how to differentiate a quadratic, and we can find out what the derivative of the quadratic is at the point x sub k. Now, finding the interpolating polynomial is going to be more difficult, so we're going to shift, as we did before, but we're not going to scale. The reason we're not going to scale is because the slope depends on how far apart the points are. If we scale in the x direction, then we're going to change the slope. So as before, we're going to shift to x equals 0 as opposed to x sub k, and we'll do this by subtracting x sub k from each of the x values. Now, the f values are left unchanged, so the slope of these shifted points at 0 should be equal to the slope of the original function at f sub x sub k. So therefore, we're going to interpolate these 3 points instead. So consequently, we will find the interpolating polynomial. And we can do so by solving this very simple system of linear equations. You could even solve this yourself on a piece of paper, and you could easily find the interpolating polynomial. We will then differentiate that interpolating polynomial and then evaluate that derivative at the point x equals 0, which will give us the slope at that central point. Thus, we would find that the interpolating quadratic is this expression here. Now, we can differentiate this expression with respect to x to get this expression here. And what we can now do is evaluate that derivative at x equals 0. Well, that gives us the constant term, which gives us the slope we see here. So that slope is probably a good approximation of the slope at 0 in this case, and originally the point x sub k. All right, so now we have an alternative formula for the derivative, an approximation of the derivative. Note that this expression is also the same as saying f at x sub k plus h minus f at x sub k minus h all over 2h. The important question now is, however, what is the error of this approximation, and is it any better than the error of the previous approximation? All right, here we see a second-order Taylor series for f at x k plus h. But the formula we have also has f at x k minus h. Well, suppose we substitute h with minus h into this Taylor series. Now, taking a look at this, we do observe that h squared negative h all squared is equal to h squared. Negative h all cubed is negative h cubed. So substituting these into that previous expression, we have this expression here. And expanding that, we have, well, almost the same Taylor series, except every second coefficient is negated. Now, for this one here, now the value of xi must lie between x sub k minus h and x sub k. All right, so now we have a Taylor series for f at x sub k plus h and a different Taylor series for f at x sub k minus h. All right, so this is our approximation of the derivative. Let's write down those two Taylor series. Now the numerator above has the first minus the second. So let's do exactly that. Let us subtract the second equation from the first equation. Now, in doing so, we immediately see that these two terms cancel each other out. But not only that, so do these two terms. All right, so what's left is, on the left-hand side, we have f at x sub k plus h minus f at x sub k minus h. On the right-hand side, we have that second term minus the negation of itself. So that's actually going to add. So that's twice the derivative times h. And then we're adding those two final terms. Now you'll notice the first term has a xi plus because that's indicating that xi plus is some value between x sub k and x sub k plus h. In the second case, xi minus indicates that that particular value must be somewhere between x sub k minus h and x sub k. So we can add those up, but they're going to be different. Now, on the right-hand side, let us factor out a third from the two h cubed terms. So we factor out a third, and then the h cubed comes out as well. And you'll notice what's left is a weighted average of the third derivative. And one of the tools says, oh, wait a second, if we that is the intermediate value theorem. All right, so we can use the intermediate value theorem to replace everything inside the parentheses with the third derivative evaluated at some point xi. And in this case, that xi must lie between x sub k minus h and x sub k plus h. All right, so now we have this expression here. Let us isolate the derivative by bringing the derivative to the left-hand side, everything else to the right-hand side, and dividing by what will be negative 2h on both sides. This essentially says now, oh, wait a second, this derivative at x sub k is the formula we found minus a sixth times the third derivative evaluated at some point times h squared. Times h squared, not times h. So this is an order h squared formula. Now what does that mean? Well, if I double the sampling rate, this means h is halved. So now the error will be dropped by h over 2 all squared, which is a quarter the previous error. So doubling the sample rate halves h, which increases the precision by a factor of 4. All right, so we can get a better approximation with a larger value of h as compared to the previous formula that was f at xk plus h minus f at xk all over h. Consequently, if we can get a better approximation with this formula than the previous one, that also means there's less impact from subtractive cancellation, because you'll recall that subtractive cancellation is caused by subtracting numbers that are too close to each other. However, if h is larger, then the values are going to be different, and not only are we evaluating with a larger h, but the points are also further apart. So again, the differences are going to be larger. Now suppose that again we want to approximate the derivative of sine of x at x equals 1 using this formula. And to 16 digits, that's the answer that we see at the bottom. Now, when h is equal to 2 to the negative 1, or 0.5, we already see that the error is reasonably small, and actually our estimation of the error, 1/6 cos of 1h squared, is pretty good already. So when we have h again, in theory the error should go down by a factor of 4. Well, 22 divided by 4 is about 5.5. That's pretty close. In fact, the ratio is not exactly 1/4, but pretty close. All right, using 2 to the negative 3, we get even better approximations. And once again, we do see that the error is dropping by a factor of 4. And with each additional step, the error continues to drop. So basically, subtractive cancellation has not yet occurred, and we are getting a reasonably good approximation. At this point, we probably don't need to continue, but let's carry on to 2 to the negative 10. And again, the error continues to drop by a factor of 4. All right, compare how good this approximation is compared to that previous order h formula we saw, f at x sub k plus h minus f at x sub k all over h, the formula you saw in calculus. This seems to do a much better job, as we've got 6 significant digits here. That's significantly better. And all we did was evaluate the function at a different point and divide it by 2h instead of h. All right, that's the power of an order h squared formula versus one that is order h. All right, the first formula we saw we call a forward divided difference formula because we only sample information to the right. The second formula we saw we call centered divided difference because it uses information on both sides of the point at which we are attempting to approximate the derivative. Now, what happens if these are sensor readings? They're taken in time and we are at the current time and we only have information from the past. Well, in this case, the best we can do is use that slope and not the other one from the forward divided difference formula. So there's a Taylor series, and with a little bit of rearranging, you can see that the derivative is this backwards divided difference formula by once again a half times the second derivative at some value tau between t sub k minus h and t sub k all times h. So this is again an order h approximation. Let's see whether or not we can do better. So this backward divided difference formula is only order h. So can we do better? Well, how about interpolating these 3 points with a quadratic polynomial, differentiating that polynomial, and then evaluating it at that right-hand point. So we're going to find an interpolating quadratic that passes through these 3 points. But again, that's going to lead to a very ugly van der Monde matrix. So as before, we're going to shift everything to 0 by subtracting off t sub k from each of the t values. Okay, so to shift to t equals 0, we are going to subtract t sub k from each of the t values. Therefore, we're going to find the polynomial that interpolates these 3 points instead. And notice that the y values are the same. So the interpolating quadratic will be similar but shifted, and the slope of the interpolating quadratic will still be the same at the right-hand endpoint, which is now 0. Thus, we will find the interpolating polynomial. But now it's easier. This is the system of linear equations we must solve, and once again, it's still more straightforward than before. Having solved it, we then differentiate it with respect to, in this case, t, and then evaluate it at t equals 0 to give us an approximation of the derivative at the right-hand endpoint. Okay. So if you were to find the interpolating quadratic, you would find this formula here. It's a quadratic in t. So we will differentiate this quadratic with respect to t, which gives us this expression here. And if we evaluate this at t equals 0, that first term disappears, and we're left with a formula of the constant term. This is the approximation of the interpolating quadratic that we see below evaluated at 0, which is now the slope at t sub k from the original data. All right, so we have a nice formula. All right, so going back to our original points, we now have a nice formula that approximates the derivative at t sub k using the values of y for t sub k minus 1, and t sub k minus 2. This is also equivalent to this formula where instead we have 3 times the value of y at t sub k minus 4 times the value of y at t sub k minus h plus y at t sub k minus 2h, all over 2h. But once again, what's the error? All right, so now we have y at t sub k minus 2h. So let's substitute h with the value negative 2h into the Taylor series. So there's the Taylor series. It's a second order Taylor series, and we've substituted h with negative 2h. Now, negative 2h all squared is 4 times h squared, and negative 2h all cubed is negative h times h cubed. So substituting that into the previous expression, we get this equation here, and simplifying it gives us this Taylor series approximation. And once again, the value of tau lies somewhere between t sub k minus 2h and t sub k. All right, in the last approximation of the derivative, we had minus h and plus h. Here we have a term with minus h and another term with minus 2h. So let's write down these two Taylor series. There's the Taylor series for t sub k minus h and the Taylor series for t sub k minus 2h. Now, that formula above has negative 4 times y at t sub k minus h plus y at t sub k minus 2h. So let's take negative 4 times the first equation and add to that the second equation. Okay, so you get that on the left-hand side. On the right-hand side, we have negative 4 times y at t sub k plus y at t sub k, which ends up being negative 3 times y at t sub k. For the derivative, negative 4 times the first plus the second gives us twice the derivative times h. Negative 4 times the second derivative in the first equation plus the second one, well, those two actually cancel out. And then we add the two error terms. Notice that the first tau is between t sub k minus h and t sub k, whereas the second error term could be anywhere, or the second tau could be anywhere between t sub k minus 2h and t sub k. All right, so that's what we have. And let's factor out the error term so that what's left in the parentheses is a weighted average. All right, so now we have a weighted average, but there's a problem with this weighted average because this weighted average does not have all positive coefficients. All right, so analyzing this error term is actually rather ugly because it's a weighted average, but it's not a convex combination. Consequently, we cannot use the intermediate value theorem, which is really unfortunate. So we're actually going to have to approximate the error. So if the third derivative is sufficiently constant between t sub k minus 2h and t sub k, then at least we can estimate or approximate the error term by just being negative 2/3 times the third derivative at t sub k, all times h cubed. This is an approximation. All right, so now with this formula, once again, let's isolate the derivative. If we isolate the derivative, bring the derivative to the left-hand side, divide by the appropriate amount, we get that the derivative is approximately equal to this expression plus our estimation of the error term, assuming the third derivative is approximately constant. Not always true, but it's good enough for the purposes where you have a system that deals with momentum. Notice again that this formula is order h squared. So in theory, we now have a backwards divided difference formula that only uses historic data to estimate the derivative at t sub k, where if we have h, then the error goes down by a factor of 4. So if we double the sampling rate, the error is going to go down by a factor of 4. So let's again approximate the derivative of sine of x at x equals 1. And there's the approximation of the error term. And at the bottom, we see the correct answer. So again, with n is equal to 1, h is equal to 0.5. Notice already that our approximation of the error is significantly worse than before. but nevertheless the error does seem to be dropping by a factor of 4. Not quite a factor of 4, it's actually dropping by almost by a factor of 5 at this point. But if we keep on going, you can notice that as h is reduced by a factor of 2, the error continues to drop by approximately a factor of 4. Not as quickly as before, but still true. Now, what's nice here is we still have approximately 6 significant digits of accuracy. So this formula is pretty close to the previous formula. The only difference is the error term. Notice that the error term in the centered divided difference approximation is a sixth times the third derivative, whereas in the backwards divided difference formula, the error is 1/3 the third derivative. So the error is about twice as large for the second formula. And again, just to reiterate, if we are dealing in space, we're going to use x, and we assume that we have information about f both to the left and to the right of x. So we can access and evaluate f at x sub k plus h and x sub k minus h. In the second, we are assuming that we are periodically sampling a signal in time, and we are at the most recent time, and therefore we only have historic data to access. In this case, we need the backwards divided difference formula, which has a larger error. However, both of these are definitely better than the order h approximations. All right, so now we're going to approximate the second derivative using similar techniques. We're going to find interpolating quadratic polynomials. We'll differentiate these twice and then evaluate these at a point. You'll recall from before that we already found the interpolating quadratic for the centered divided difference formula. We can differentiate this twice with respect to x, and that gives us that first coefficient, which is, it's already a constant. Well, a quadratic has a constant concavity, so that concavity will be the same everywhere. All right, so that is our formula for the second derivative. So here we have a formula for the second derivative. And this is, of course, equal to this formula where we're using x sub k plus h and x sub k minus h. So once again, we have to ask ourselves, what is the error? All right, so this formula has one expression with plus h and another with minus h. So as before, let's write down the two Taylor series. So there's the expression, or the Taylor series for plus h and the Taylor series for minus h. Now in the above expression, we have the plus and minus h terms being added. So let's add these two expressions or equations. So the left-hand sides get added, the f at x sub k's get added, so it's twice f at x sub k. The derivatives cancel each other out. The second derivatives add up to give the second derivative times h squared. The third derivative expressions cancel out, and we add the error terms. All right, now let's factor out a multiple of the error term in order to get a weighted average of the fourth derivative. So in that case, we factor out a 1/12, and now we have a convex combination, in fact, the average, of the fourth derivative evaluated at 2 points. Consequently, using the intermediate value theorem, we are guaranteed that there exists a psi such that that more complex expression equals this simpler expression. All right, nice. Just a reminder, psi lies between x sub k minus h and x sub k plus h now. So we can isolate the second derivative. And if we isolate the second derivative, notice that we get the formula plus an error term where psi lies on an appropriately small interval. Notice that the error term is multiplied by h squared, so this formula is also big O of h squared. Double the sampling rate, halve h, the error goes down by a factor of 4. Alternatively, you could go the other way. If it's too accurate, this may suggest that you can actually decrease the sampling rate without adversely affecting your results. You don't always need very precise values. So now let's approximate the second derivative of sine of x at x equals 1. And the correct answer to the given number of digits is shown below. Well, when h is equal to 0.5, well, it's actually not bad. We get the first digit correct. With dividing h by 2, we get a better approximation. In fact, you can see that the error is already dropping by almost exactly 1/4. Again, with each subsequent approximation, the error is dropping by 1/4. Divide h by 2, and you can see that the error does again drop by a factor of 4, and so on and so forth. And we are getting better and better approximations of the result. So that's pretty good. And not only that, take a look at how closely our approximation of the error estimates the actual error. This is important. Now, in the real world, you don't know what the actual appropriate derivative is, but what's important is that this gives you faith or trust that the formula does work, again, so long as there is sufficient momentum in the system so that the higher derivatives are not wild. With 2 to the negative 10, we've got a pretty good approximation. So taking a look at that, we've almost got, wow, almost 7 digits of accuracy. That's pretty good. All right, so let's say we have only historic data. Well, previously we did find the interpolating quadratic that passed through these 3 points, and so instead of differentiating it only once, let's differentiate it twice, which gives us that constant, and that's our formula. Okay, not a problem. All right, so we have this alternative formula for the second derivative, and it's equal to this expression here. What's the error of this one? All right, so in this expression, we have a y at t sub k minus h term and a y at t sub k minus 2h term. Let's write down both of those Taylor series. So from before, we have this as the first one. However, we're only going to write a second order Taylor series, with the third derivative being the error. And there's another second order approximation of the second one. Now, in the formula, we have -2 times the first left-hand side plus the second left-hand side. So let's have -2 times the first equation plus the second equation. The only things that cancel out now are the derivative terms. Everything else remains in some way, fashion, or other. All right, so now let's take those error terms and combine them so that we have a weighted average. Well, there's our weighted average of the error terms, and you'll see that one coefficient is 4/3, the other coefficient is -1/3. So unfortunately, it's not a convex combination because all of the coefficients are not positive, and therefore we cannot use the intermediate value theorem to simplify it. Instead, we can say that as long as the third derivative is approximately constant within the vicinity of t sub k, we can approximate the error term as follows. It's simply the third derivative evaluated at t sub k all times h cubed. All right, so that's the formula we just found. Let's isolate the second derivative, and we get that formula there. But the formula is order h. Notice that the formula is the same formula as before. It's 1 times the value on either side minus twice the value in the middle all over h squared. But when we were approximating the derivative at the midpoint, the error was order h squared. Now that we're approximating the error at the right-hand endpoint, the error is only order h. All right, once again, let us approximate the second derivative of sine of x at x equals 1. The third derivative evaluated at 1 times h is the estimation of the error, and we calculate the error relative to the exact answer shown below. So with h is equal to 0.5, we don't start off with a very good approximation. It's almost 100% relative error. But we are slowly getting better with by having h. And the error does seem to have actually dropped by almost a factor of 2. Have h again, the error drops again by approximately a factor of 2. Remember, this formula, even though it's identical to the previous one, because we're using it to approximate the derivative at an endpoint, it's now only order h. And so having h only halves the error. So if we keep doing this, we do notice that, as before, the error drops by a factor of 2 with each additional iteration. And the precision isn't that good in the end. We have 2, maybe 2 and a bit digits of precision. So this order h formula isn't going to work. Consequently, if you want a backwards divided difference formula that has an error that is order h squared, we must resort to interpolating 4 points, not 3. And once again, the weighted averages of the errors is not going to be a convex combination, as some of the coefficients will be negative. So once again, we would have to end up assuming that the fourth derivative is approximately smooth, in which case the second derivative at t sub k is approximately this linear combination of the 4 y values, and the error term is approximately 11/12 times the fourth derivative at t sub k times h squared, assuming that the fourth derivative around t sub k is approximately constant. All right, so let's try it again. Approximating the second derivative of sine of x at x equals 1. There's our approximation of the error term, and down there we see the correct answer to the given number of digits. So with h is equal to 0.5, well, not very good, but better than the previous version. And once again, notice that the error is dropping not by a factor of 4, but by a factor of 3. But as we make h smaller, it does seem like the error continues to drop by a factor of 4. And notice that our approximation of the error is pretty close to what the actual error is. So carrying on, we get better and better approximations. And with h is equal to 2 to the negative 10, it seems that once again we have 6 digits of precision. So pretty nice. Comparing these, the first is the centered divided difference approximation of the derivative and the corresponding error term. The second is the backwards divided error difference, and once again we see that the coefficient of the error term is twice that of the first formula. Now, if we look at our approximation of the second derivative for the centered divided difference formula, the error term is -12th times the fourth derivative. However, the backwards divided difference formula is approximately 11/12 times the fourth derivative. Again, times h squared. Notice that now the error is increased by a factor of 11. So if you're only using data on one side of a point, you will not get as accurate an answer. But if you are dealing with a real-time system where you only have current and previous data, then you can only give information about the current time by using the backwards divided difference formulas. So, following this topic, you now are aware of numerous different ways of approximating the derivative and the second derivative of an expression when all you have is sampled data. You understand that the error should likely be order h squared for the formula to be reasonable. And you have seen order h squared approximations that are both centered, meaning using information to the left and to the right of the point, as well as backwards divided difference, which uses only information that is historic. And finally, you have observed how these formulas actually work by looking at examples where we do indeed continually divide h by 2 and observe that the error does go down by either a factor of 2 or a factor of 4, depending on whether or not it is order h or order h squared, respectively. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!